this bell ringer to build up our understanding, update our notes for future forgetful selves. I'm still talking. Thank you. So, right here, I think a lot of us remembered that in order to make the function invertible, what did we have to do?
Restrict the domain.
We got to restrict the domain, and that's part of the problem. But why did this group, why did all the groups take out literally half of the parabola?
Because that's what you told us to.
So why?
So we can pass the vertical line test.
And the horizontal.
So in order for that function to be invertible, it has to pass both the horizontal and vertical. Now remember, the vertical line test is just if it is a function, right? So the vertical line test helps us assess if that relation is a function. The horizontal line test tells us whether the inverse is a function, right? Originally, if I drew a horizontal line, how many times did it intersect the parabola? Twice. So when we reflect this, right, which we're going to do in a second, if I were to reflect this entire parabola, that vertical line would touch the horizontal parabola how many times? Twice. So the inverse would not be a function. We'll look at that in a second. However, if I've gotten rid of this entire half, how many times does that horizontal line now touch the function?
Oh no.
Once, right? So it's not just that I told you so. What we've done is we have restricted this function to make it, so restricted domain to make f of x equals x plus 1 squared minus 4, what? We said it has to pass the horizontal and vertical line test, but there was a name for functions that pass both horizontal and vertical line tests.
A 1-1.
Right? So we had to make f of x 1 to 1, right? Passing vertical line test and horizontal line test. So that's it, right? We got rid of half of the function. We restricted the domain so that the function would be 1-to-1, passing the vertical and horizontal line test. Now it's invertible. Now, if we look at this, some people wrote the interval notation. And you're going to have to do this on your demonstrated understanding. Literally, when we say domain, what are we talking about?
The x value.
The x values. If I look at this restricted function, what is the lowest x value?
I can really use it.
This vertex, remember, that's where it starts. What's the lowest x value? Negative 1. Does it ever quit going to the right?
Nope.
So the greatest x value is?
Infinity.
So minimum x and maximum x. The one thing I would point out is on this negative 1, we do need a bracket, because do we actually have the value negative 1? Does the function ever get there?
No.
Isn't that a closed point?
Oh, yeah.
The vertex, right? That vertex is a part of the function. So it would be a bracket for the interval notation there. And by the way, because someone asked me about this first block, that is the interval notation. When we say interval, it means everything from this minimum up to this maximum. It's that entire interval. That's just an interval notation. Okay. Yes, ma'am.
That's it?
Nope. We still got to talk about this part. And I want to do one more thing to help us prepare for the demonstrated understanding. Really quickly, I do want to note, why does it make sense that this is my vertex based on this equation?
Oh. I know.
Because H and K.
Because of h and k. What form do we have? Vertex form. So why did plus 1 become negative 1?
Because it's inside the parentheses.
So we needed the opposite. Yep.
Yep.
So the vertex literally should be negative 1, negative 4, which is what we see graphically, right? These things that we've learned in the past have not gone away. They're still holding true. But what I do want to point out, because you will have to do this on your demonstrated understanding, how would I graph the inverse function, right? I've restricted the domain. I'm not looking at this half anymore. I'm only looking at this half. How would I graph that inverse function?
Oh.
Something with transposing, right?
You go like.
So, okay, so one, what do we know, and this is important, I'm going to bring these ideas together. What do we know about every set of inverses? Something about y equals x. What's happening with y equals x?
It'd be multiple.
It's not transposing yet. If we're talking about the line y equals x, what do we do with y equals x? Say what? So there's my line, y equals x. I mean, yeah, but what are we going to do for the inverse function? Starts with an R.
Reflect.
Say it again.
Reflect.
Didn't we say all inverses are reflections across y equals x?
Yeah.
And because it's a reflection across y equals x, what happens?
Everything.
They transpose
What do?
the inputs and outputs.
So, remember, when we talk about an inverse function, the reflection across y equals x causes my inputs and outputs to transpose. So let's look at this. So what is this point currently?
Like what's right now?
Yeah, whatever right now.
-1, -4.
-1, -4. So when I transpose it, sorry, I'm looking for a marker.
-1.
-4, -1. And so I go to the left 4 and down 1. Now,
And then what?
well, I would go to my next point. Tell me to stop because I get to another point.
Stop.
Right? And technically I will point out, that's a point 2, but do I know what those coordinates are?
No.
No, so I'm just going to the nice easy coordinates. That is 0, -3. So what would I get?
3. Wait. -3, 0.
Now, I do want to point this out. I'm going to come back to this in a second. Or I'm going to come back to the graph in a second. Does anyone know, though, another mathematical representation that could help me stay organized with my
Chart.
points? A table, right? If I'm looking at x and f of x, this original point was -1, -4. This point,
0, -3.
okay, I'm going to go to the next clear point, which is right here, which is,
1,
and I'm going to keep going, it's 2, 5. Okay? So now I want the inverse. Now, I will remind you, because some people looked at me like I was crazy today, even after I talked about it, during the demonstrate your understanding. This superscript of -1 just tells me what?
The F inverse of some. I remember what you said.
You just say an inverse of f of x.
Yeah.
That's all you have to say, right? When you see the superscript of -1, I'm just saying the inverse of f of x, the inverse function of f of x. Right? So Jaylee, what are we going to do to go from this table to this inverse table? Can I help you learn some, or you're out today? Okay. I would love for you to engage and learn something. Carly? Okay, so I transpose what? The x and the y, the inputs and... So what would this -1, -4 become? What about this one? Okay, Brendan, what about the next one? Come on, what are we trying to do? Why is it 0, 1? Okay, I need you engaged though, because you look at me like deer in headlights. Come on, we gotta stay involved. Tristan,
0, 1.
I know I got you, but I need everybody engaged, looking, talking, thinking about these things. So we transpose the inputs and outputs. So what would the last one become?
You can't let me carry my rule. Me, you guys, and me. Oh, it's 5.
Just in general, 5, 2.
I
So-
don't know, I think you.
We just graph those points now. -4, -1, -3, 0, 0, 1, and 5, 2. 1, 2, 3, 4, 5, 1, 2. Now, I want to caution you, because a lot of students, and I already saw it on the demonstrated understanding from first block, make a very small, careless error here. This point right here was the what from the original function?
The reflection.
Yes, it was a reflection across y equals x, but I just meant, if I just look at the original function, what would I have called this point? Starts with V. Wasn't that the original vertex?
Yeah.
So when I draw this curve right here, this is the what of my parabola? The vertex. So am I going to go past it? No. You stop at the vertex because that's where we stopped right here. Alright, there's my inverse function. All I had to do was transpose my inputs and outputs. Say again, Zakai.
Okay.
Okay. Notice, you don't have to make a table, but does a table help me stay organized and make sure I get the right transposing?
Yes.
Okay. I highly recommend it. You don't have to do it. So, we have one more thing to do. We have to determine the equation of the inverse function. First off, do you remember what the name of this type of function like this was? I introduced the language yesterday.
What you said?
What the name of this type of function, this inverse of a quadratic is? So remember the quadratics, right? X squared, x cubed, those were the power functions. So it is the inverse of the power functions, but we need to remember the name of it. So let's look at this, okay? We have this equation. We have, technically it says f2 of x equals x plus 1 squared minus 4. This notation is what you'll see based on the calculator, but remember, when we say f of x, what do we really just mean by that?
Variable function.
No, just f2 of x, like f of x, g of x, h of x, that's just the... So x is my blank, the whole thing is my blank.
X is your input, and the whole thing is, I don't know.
Well, you have an input and an...
Output.
Okay, there you go, right? X is the input, f2 of x is the output, and what variable do we use for outputs?
K. No, I'm saying why?
Y, right? K was just the output for the vertex.
I was just saying, I was told.
So, we have not gotten to extraneous yet. Okay, so hold on that. But, I want the inverse. And what's that foundational piece of all inverse functions? It's a reflection across,
Well, X and Y.
well, y equals x, which causes what to transpose?
Inputs and outputs to transpose.
So what does this y become?
X.
X.
Just becomes x, right? I transpose, and I'm left with y plus 1 squared minus 4. But if I wanted an inverse equation, right? If I want an inverse equation, what do I need the equation to equal? What do I need on its own? Now for an inverse equation or inverse function, that's to look for a 0. What do I need? I don't want x equals, I want y equals. For the function, for the inverse, I need what y is equal to. So what do I got to do? What do I need to use in order to get what y is equal to and get rid of all the stuff around it? Huh? So that's part of it to help me think through it, but I can't use order of operations to simplify it. There's nothing to simplify here. So I can do a square root. What is that? It's the inverse, right? But I can't do a square root yet, because what's happening to y? It's being added by 1. What's happening to y plus 1? It's being squared, and what's happening to y plus 1 squared? Minus 4. I could only do the square root if that was the last thing. What's the last thing being done?
Subtraction.
Subtraction by 4, so what do I need to do?
Add 4.
Add 4. So x plus 4 is equal to y plus 1 squared. Now what could I do? Square root, right? I have the square, the last operation is a square, so I need a square root. Those are inverses, so they cancel. So what's on the left-hand side over here? What's on the left-hand side of the equation? It's not a number. It's what?
You said it's not a number.
Yeah, I mean, it's a variable, right?
Right.
I'm just left with an x.
No, X plus
Square
4.
root of X plus 4.
This, listen. Okay, so hold on to that idea. We got to remember, like, it's literally the square root of x plus 4. You don't have to make it fancy. I know some students were trying to do x plus 2. Where do you think they got the x plus 2 from? The square root of the 4. But you cannot do that. Do not take the square root of different terms. To illustrate that, so I'm pausing on this. I'm going to come back to it. Taking the square root of a single number inside of that is like this. What would the square root of 9 be? 3. What's the square root of 16? 4, right? And 3 plus 4 is?
12.
Plus.
7.
7. Plus, not times. But let's look at this again. What is 9 plus 16? Because I know order of operations. I can add those. It's what? 25. And what's square root of 25?
5.
So can I do it either of those ways? Can I take the square root of 9 and the square root of 16 and add? Is that correct?
No.
Can you say that?
We do not get the same answer, so that is not an equivalent way to do it. You cannot take the square root of individual terms, things being added or subtracted. So I would just leave it as the square root of x plus 4. You cannot take the square root of terms. You can take the square root of factors, but not terms. Okay? And so what is the square root of x plus 4 equal to? It's what? Let's say, only just left with that y plus 1. Now KB mentioned earlier the plus or minus. But if I want an inverse function, and this is what you have to be careful about. If I do the positive and the negative, do I just get this top half? Remember how we got the top half and it would also give us the bottom half. So if I want the inverse function, do I want positive and negative? No. Because I've restricted the domain, I only have the positive. Okay. Last detail. I don't have y equals yet, what do I need to do?
Figure it out. Inverse.
Okay, what inverse am I going to use? What's happening to y right now?
Just can't.
It's being added by 1, so what do I need to do?
Subtract.
Subtract 1. That's it. Guys, it's y plus 1, I need to subtract 1. And so, please notice, am I taking the square root of this 1 here? Is there a square root with it?
No.
So is that negative 1 going to go underneath the radical?
No.
It is the square root of x plus 4 with the minus 1 outside. Okay,
Where you get minus 1 from?
because remember how we subtracted 1 here to make a 0? And whatever I do to one side of the equation?
Do to the other.
But it's not, that's what I'm saying, it's not under the radical, so it has to go outside of the radical. Notice a word I keep saying is actually the name of this type of function. It's a radical function. These functions that are inverse of power functions involve what symbol? A radical. Either a square root, a cube root, a fourth root, but they are radicals. So those inverse of power functions are called what type of function? Radical functions. The inverse of the power functions are called what again? Radical functions. I'm going to go through the proficiency scale in just a second, but then I also want you to update your Freire models and your knowledge for whatever you need to. So looking at these, looking here, have we looked at restricting the domain of a function to make it invertible?
Yes.
We did that even just this morning, right? Composing two, or this afternoon at this point, composing two functions to determine if they are inverses. Have we done that? Have we talked about that? Does that language sound familiar? No. We have not done it, and honestly, we don't have time, so if you want to, you can scratch that out. Okay? I'm going to save us some time by not focusing on that idea of composing to determine if they're inverses. Say again? Does it not say inverses on there? You say it's the wrong paper, Tyler? What does it say at the top? Does it say this? Unit 6 inverse functions?
Yeah, you don't got none of that on there.
Restrict the domain. Compose two functions. It does. It's just I have only 3 and 2 up there. I don't have the 4. Alright, have we looked at determining if two functions are inverses graphically? How do we know if they're inverses graphically? Well, that's if it's invertible, but how do we, if I give you two functions, how do you know if they're inverses based on the graph? A reflection across what? So if they are reflections across y equals x, they're what?
Functions, inverse.
Well, they are inverses. The reason why I would caution that is this, right? That's not invertible, but that is its inverse, is it not? It's just not a function. So if it's a reflection across y equals x, it is the inverse. It may just not be an inverse function. Okay? So if it's a reflection across y equals x, it is the inverse. Which also means the inputs and outputs have what?
Transpose.
Transpose, okay? Have we graphed inverse of functions graphically or tabularly?
Yes.
Yep. Have we solved equations for the input to determine the inverse function?
Yes.
That's literally what we did here, right? We solved for the input, we solved for y to figure out what the inverse equation was. Alright, I'm going to erase this here. Have we talked about inverse of a function? Power functions? Invertible functions? Composition of functions?
No.
No, but that's the one I just told you we're not talking about, right? So you can scratch that one out. One-to-one functions.
Barely.
Barely, but yeah. Well, we talked about it yesterday and today, right? If it passes the horizontal and vertical line test, it's a one-to-one function, and it has to do that to be invertible. That's the big priority. Radical functions. So if it's the inverse of a power function, if it involves a square root, a cube root, a fourth root, it's a radical function. That symbol is called a radical, which is why what was underneath was called what again?
Radicand.
Radicand, right? Like they're all connected ideas. Transposing. Have we talked about that like a whole lot? Yeah. Features of functions. We haven't done that much here, but what do I mean by a feature of a function? So if we want to identify the features of functions and their inverses, I'm talking about the domain, range, in behavior, intercepts, etc. That's all I'm talking about there. Okay? Have we talked about extraneous solutions? No, we will have to do that after this demonstrated understanding though, and do it a little bit later.
Cross it out or no?
No. Hey. Yeah, I know. He walked out and I tried to grab him and then he was already gone. Yeah. Do you need it right now or could we send it at lunch? Okay. Yeah. Gotcha. Cool. We'll do. Alright, bye.
Can I take you so I can wake up?
Sure.
I don't even need my phone. I do need some drink. Oh, me temperature, I had me so cold.
Okay. Thank you, KB. Alright.
Hey, what you?
Mr. Armstrong.
Okay, I'm already doing that.
So, determining if a relation is a function. How do we know if it's a function? One input maps to one and only one output, that vertical line test, and determining if a function is one-to-one. So here's what I want you to do. I want you to reflect and look at the proficiency scale. If you can't just know it off the top of your head, you can't do the skill, don't mark it off, but maybe update your Frere model based on the information we have on the vertical surfaces so that you can be prepared to use those notes later. So I'm going to give you all about 5 minutes to update your notes to your future forgetful self and make sure you have everything you need. Not just writing down what we did, but explain why. Always make sure you can explain why. If you cannot explain why, it's going to be a rough time. Yes, Janai. And I'll be more than happy to answer questions during this time as well. What's up, Janai? Okay, that's not like what?
Hey, can I go to the bathroom?
Say again? No, ma'am. That's you can't say everything.
I'm watching.
So why would we not ask a question before right now? Move up there. Did I tell you you had to be in this group
My name from that.
today?
But he got away
I guess I did say commission. Move up to where you can see it. I don't care at this point. We literally have a whole group that's in open. Janai, what's your question? Okay, so you understand something, you can't just say everything, can you? But what? But remember, reflecting across y equals x causes the inputs and outputs to transpose. I would like the line y equals x, but can you just switch the x and y values without y equals x in there? Okay, so you know how to transpose inputs and outputs. So just do that.
That's understanding.
If you show me that that's what you're doing, or explain it. Now, if you draw the line y equals x, that's better understanding, but if you transpose your inputs and outputs, like make it, remember how we made a table to transpose inputs and outputs? Write that down. right? As an explanation of what you do. So Ty, you need no notes to your future forgetful self? Nothing that you need to update? Just trying to help you out. Bree, you could have done like so many notes during the time that you drew that all over the desk.
I did.
Is that from? Okay. It's your choice. Do I need to clarify or add anything based on questions we have? Yep. Huh? Yes, but we're about to continue forward. You could have been writing some of the stuff, right? Like this right here is getting inverse functions algebraically. That would have been this section, right? Inverse functions graphically and tabularly. That was all of that conversation about transposing the inputs and outputs. There's still a lot of it there on the vertical surface. We're about to do features of inverses. And you can ignore that part because we're not doing that part. Yeah.
Can I use one of these?
For what? What's your prayer model?
She already don't wrote them.
You what?
She already wrote them. Okay.
Do I say, can I use one to write down that second?
But where's your prayer model? That I gave you yesterday.
I want to use it.
Did I give it out yesterday or 2 days ago?
You got it on
2 days.
Wednesday.
I gave it out Wednesday. For your Wednesday?
Yes.
So where is it?
Let me check.
Okay. All right. Okay. I need you, while a few of us are finishing up our notes to our future forgetful selves, I need you to get out the textbook pages, right? I think this was somewhere where we're going to be is in activity 2.2 actually. I think this was page 30 or so. I would keep out your prayer model to add some other things, but okay, I think it's M3-30. There you go. Is that activity 2.2? Perfect. Oh, I completely lied. It is not 30. It is 24.
You talking about these?
Yes. Wait, which one does that say? Yeah, it says inverse functions. Wild. What are we studying right now?
Inverse function.
Okay. Okay. So, we're going to do a little bit more practice with this. We have to do it together instead of individually, but I need you engaged, taking what notes you need to. We're not going to do all of this, okay? This is, again, number 1 on page 220. Actually, I'm focused on H, so this may be 225. It's just the next page. So you need 24 out, but we're going to focus on the questions with 25. Okay? So yeah, it's the questions on 25. There's a lot that's earlier, but I'm focusing on H and I. All right. So first things first, is this function invertible? Wow. Does it pass the horizontal line test?
No.
I mean, no, no.
Right? It does not pass the horizontal line test. I got to restrict it. How am I going to restrict this function? Okay, so the left side, so tell me when to stop.
Where you at?
Stop.
Right there, right there.
Stop where?
Right there.
What's that point?
The verse
Four.
of
So stop at the vertex, right? Right? We go all the way to that vertex. Now, this is the point 0, -4. That's the vertex. So what is my domain restriction? What's the only domain that I'm actually using? The right side, but what is the... But listen, when we use interval notation, I always need a minimum and a maximum. So what is my lowest domain value? We gotta remember domain is x, right? So my minimum x is 0. What's my maximum x?
Infinity.
Does it ever quit going to the right?
No.
So the maximum domain is infinity. Alright? And so Janai, you're asking about that whole graphing thing, right? If I have to have that line y equals x, do you? No. Is it good? Do I recommend it? Yes. But guys, how can I easily graph the inverse of g of x? How can I easily graph the inverse of g of x?
Y equals X.
So y equals x, I already restricted the domain, but I will point this out. I used a different representation.
Table.
Can I make a table that helps me organize my thoughts?
Yes.
Yeah, 100%, right? I've got x and I've got g of x. So what are some points on g of x for my restricted domain? When the x is 0, the y is negative 4. Give me another point.
2, 0.
So there is a 2, 0, but there's one even before that. 1, negative 3. You know, you should have these pages as well, right? 2, 0. Are there any more that we can easily see? I think 3, 5 is one as well.
Yep.
Alright.
Now, I want x and the inverse of g of x. So, transpose. Okay. So, negative 4, 0, negative 3, 1, 0, 2, and 5, 3. There's my square root or radical function. Okay. Now, when we come back, okay, we're going to write this equation in just a second, but I want us to notice something. You don't have to know this fact to get these questions right on the demonstrated understanding, but I want you to notice right here. With my original function, what's my domain? We have a domain restriction. What's my domain? 0, 2. Okay, going to the right. What about the range? The range is not the x, the range is my y. So what was my minimum y? What? Well, no, which one? There's only one of them.
Negative 4.
The minimum y was negative 4. What's the maximum y? It keeps going up, right? Now let's look at my inverse function. There's a really cool pattern here that I want us to see. What's the minimum x for the inverse function? The minimum x is negative 4, right? It never goes past here. It stops. And what's the maximum x? Positive infinity. Uh-huh. What's the minimum range value? What is it? Remember, range is my y, so I need the minimum y, which is what? 0. What's the maximum y? Does anyone see anything interesting about those domains and ranges?
Oh, they swap.
Ah, they swap.
They transpose.
Well, so I know it's going to sound goofy. The inputs and outputs, the individual values transpose, causing the domain and range to switch. So we wouldn't say the domain and range transpose. We do say domain and range switch. But notice what was the domain became the range, and what was the range became the domain. Let's look at this one more detail. I had originally the y-intercept 0, negative 4. What's that y-intercept going to become? An x-intercept of what? Negative 4? Is that what we see right here?
Yeah.
I originally had an x-intercept of 2, 0. What's that going to become? Is that what we see right here? So, we need to know that our inputs and outputs transpose, and so those features switch, right? The domain and range switch, the intercepts switch. And that's all we're going to do for the demonstrated understanding. When you come back from lunch, we will start the demonstrated understanding.
You got too much good today?
Yeah, so
My dad's watching the car right now. You see.
I know you ain't talking.
Tyson, let's go. We got to get
If we make it, get something, you set the board.
Yeah.
said I got mixed up. Look at that, what you did.
Thank you, Dave. Thank you, Kyson. Thank you, Dewan. Thank you, Sean. Oh no, I don't have enough books. It's okay. Hey, Julie, come on. Sarah page that book. Let's go. Eisenhower's here. So a couple of things that I want to talk about. This is the very first quadrant on that new Frere model that I just gave you. It should say linear versus exponential functions. This should be a recap.
So just write down everything you said, bitch. I'm finna record it. Bang!
I'm already recording. So, linear versus exponential. What do we remember about linear versus exponential functions? Hey, one person at a time. Can only get one.
You wanted to see you?
So we'll go Nate and then we'll
Shut
go
up.
Cam.
Oh, well, I'm gonna
Standard, factored, and vertex.
Right, is that correct? Exponential has three forms. Standard, vertex, factor. Wait, say that one more time. Cam, say it. That's quadratic. Quadratic has those three forms. Okay? It's okay, learning's a process. We make mistakes, we grow and get better. What else do we know?
Exponential is multiplying.
Ah, exponential. It's not just multiplying, it is constant, multiplicative what? Constant multiplicative rate of change. Remember, this is the only non-additive rate of change that we have studied, right? This is the only one that's not additive, okay? It's a constant multiplicative rate of change, which is why the equation was what?
Exponential.
Yeah, but that's the type of function. What's the equation?
Oh, A times B X.
So, A, sorry, can someone let him in? Times B to the X. Remember, yo, chill, counsel. Constantly multiplying. What mathematical operation shows repeated the Y? Counsel. Stop drawing and pay attention and learn something. What operation shows repeated multiplication?
Exponents.
An exponent, which is why the exponent is a variable, right? That indicates that we are repeatedly multiplying constantly, without end. So that exponential is that constant multiplicative rate of change. F of x is equal to a times b to the x. How did that compare to linear? Had a constant additive rate of change. Remember, these are the only functions that had a constant rate of change, right? Eventually with polynomials we got to constant, but only the exponential and the linear had a constant rate of change right away. And so for a linear, what was the equation?
Y equals mx.
Okay. And remember, what operation shows repeated multiplication, or repeated addition? Multiplication, that's why it's m times x, right? That repeated addition is shown through multiplication. Okay, these are the big concepts to remember. Shape of a linear is quite literally a line. Shape of an exponential
Oh, yes.
is that exponential curve, right? Now remember, it could go to one of two ways. We're going to talk in just a second about which direction it goes based on some details, okay? So that's that first lesson I had you tear out of the textbook, Half-Life. If you want some more other than just that, they do have some more information. But those are the features, the keys that we need to know. Yes?
Why are you redoing Unit 2 stuff?
I'm not redoing Unit 2. I'm doing a quick recap in 2 minutes about these ideas because we have now studied the inverse of the power functions, right? The inverse of polynomials. What were the inverse of power functions? It was started with an R. Radical functions, right? That's what the demonstrated understanding was just on. But what type of function have we studied that we haven't done the inverse of yet?
Exponential.
Exponential. Anybody want to take a guess what we're going to call the inverse of an exponential?
Yes.
Why don't you look at that Frere model real quick?
Oh, logarithm.
Oh, a logarithm, a logarithmic function. All right, so I'm telling you right away, right, what I need you to learn out of this, okay? So, right here, okay, we're about to cover the ideas from lesson 2. Starts on M3-107, but we're not going to do it from the book pages. So you don't need to go to the book pages. There's some more information in the book, but we need to just look at it. Other side. Right. Exponential functions and their features. Okay, so I need you to look at this. What type of function is this?
Exponential.
Exponential, right? Notice, do I have an a in this case? No, I just have the b to the x, right? Remember, what was the a? It didn't define the type of function. The a was not the vertex. We don't have a vertex.
Concavity.
Not the concavity. We don't have concavity.
Slope.
No.
Is it exponential?
So remember, here's my equation, right? This is what I'm repeatedly multiplying by. That's my rate of change. There we go. That a was my y-intercept.
Right.
So,
Y-intercept, yeah.
okay. So I'm just not worrying about the y-intercept this time. I am focusing on the idea of a constant factor. And what I want us to know is the difference between these two exponential curves. This is called an exponential
Curve.
Negative curve.
Graphic curve.
Well, first off, notice how it's increasing as we go to the right? So we call it a what? Growth.
Positive curve. And growth.
It's an exponential growth. This one is an exponential decay.
You do that?
Degrowth.
Oh.
Okay? So exponential growth, exponential decay. Okay? So it's growing or it's decaying. And what I need us to quickly see is when is it growing and when is it decaying?
Oh, they're growing.
Sorry.
Decreasing.
Huh?
Wrong when it's showing.
You weren't raising your hand? Okay. Alright. So I'm going to move this up here, or try to. Okay. It's hard to see maybe, but what is my b value right now?
1.
1.6. And right now, that exponential curve, is it growing or decaying?
Growing.
It's growing, right? So if I continue making b bigger, notice what's happening to that exponential curve. What's it doing?
It's decayed.
What's going up faster?
So it's, when you say it's growing fast, or it's growing faster, is essentially what you're saying, isn't it getting steeper here? Because what am I repeatedly multiplying by now?
3.
I'm repeatedly multiplying by 3. What's going to happen? What's going to grow faster? Multiplying by 3 or multiplying by 2? Multiplying by 3, right? So when that b, that base gets bigger, it grows faster. Well, when do you think it's going to stop growing? At the negatives maybe? When it gets to 0? Okay, there's 1.1. There's 1. Oh.
Oh, something like that.
When is it decaying? When it's below 1. Do note, I cannot go below 0. You know how it's no longer exponential? If b becomes 0, it is no longer an exponential function. So when is an exponential growth? When b is greater than 1, right? If you multiply by something bigger than 1, what's it going to do? It's going to grow, it's going to get bigger, right? If it multiplies by more than 1, it's going to grow, it's going to get bigger. And what's going to make something smaller? If it's between
1 and 0.
1 and 0, right? If I take 16 and I multiply it by a half, what do I get?
8.
8. See how that got smaller? If I take 16 and I multiply it by a fourth, what do I get?
4.
4, right?
Quick math.
Okay? So, it's an exponential decay if my base is in between what? 1 and 0. So, if my base is between 0 and 1, it makes the number smaller, right? It decays over time. If my base is greater than 1, it's growing.
And I'll put this in the first box.
Wait, say that one more time.
The exponential growth is when the base is greater than 1, right? If I multiply by something bigger than 1, it's going to exponentially grow. If the base, the constant factor, is between 0 and 1, it's going to decay. Just in my explanation again was, if I take 1/2, which is 1/2 bigger than 1 or between 0 and 1?
You said if the base is greater than 1.
No.
1/2. Is that bigger than 1 or is that between 0 and 1?
Between 0 and 1.
That 1/2 is definitely 0.5. That's between 0 and 1, right?
Yeah.
So that's going to cause things to decay, right? Remember I gave that example earlier. What is half of 16? 8. What's half of 8?
4.
What's half of 4?
2.
What's half of 2? What's half of 1? 0.5. See how it's getting smaller every time?
0.35.
So it's exponential decay. Yes, Cam.
You said the base.
Yes, ma'am.
What's the base?
Let's have 0.5. 0.45.
Base exponent.
Oh.
So when I'm talking about 3 to the x, my base is 3, variable exponent. So another way to say base, Cam, that's my constant factor. Whatever the base is the constant factor.
Yay.
Okay?
Hey boy, go down over. Alright now.
Oh, sorry, I meant to show you this earlier. Notice, if we get less than 0, is that an exponential function still?
Yeah.
Does that look like this?
Yeah, no.
It's got a curve, but does it look like this or does it get like super funky?
Oh,
Super funky, right? So can my constant factor be negative?
nah.
No. The constant factor cannot be negative. What else can the constant factor not equal? It cannot equal 0, and it cannot equal 1. Do notice the constant factor, make a note of this to yourself, constant factor can't be negative, equal 0,
What box
or
you put that in?
equal 1.
What box you put that in?
Top left. Actually, no, top right. Sorry, exponential functions and their features.
Can't be.
Can't be negative, cannot equal 0, or equal 1. Okay? I may have forgotten to check homework today. I will guarantee check to see if you have just completed this table on Monday. Notice, page 110. Look. Hey guys, pause for 1 second. I need you to recognize for both of these functions, the basic exponential growth and decay, they both have 0 to 1. Do they get to the x-axis? No, right? Notice this is true for any growth or any decay. It'll have exactly the same features here. Do not worry about asymptote. I'll talk about that on Monday. Don't worry about asymptote. I'll talk about that on Monday. Yes, sir. Yes, so I was realizing, thinking about it, that we were asking the wrong question. So if I have minus 2 squared plus 4, then I would put that 0
It's not even a big
Who phone is?
So you had another one of my calculators. I know. So you can imagine root, we took the square root of a negative. However, I can minus the square root of x too. Negative 4. Can I square it? What's up, doing?
You just had calibrate.
So you can square
Stop pushing 20 still in high school.
when we talk about radical equations, radical functions, you can't have an imaginary because we're not taking the square root. Does that make sense? So yeah, you cannot have imaginary roots because just follow that. So Tyler, did you just wake up and look at the solutions like this minute? Or did
Hey,
you-
Ashton,
Oh, when I saw that was Tuesday.
this today your last day? I gotta show you your picture that's on your phone.
It was an odd geometric one though. It was. When I saw that, I don't know. I can't believe. Also, I was really confused. 'Cause I thought you were talking about Pearson's correlation. I didn't realize that Pearson's correlation of skewness. Like I've never seen. I mean, obviously. No outliers, but it's heavily skewed to the right. So
Bang, bang, bang,
they're not doing
bang,
it.
bang.
I engaged. It was a good. I thought it was a doable test. Like I think it's a
Cam.
test where everyone can yeah.
Walk back in front of the camera.
Some crazy
see that.
Hey,
Come on,
I ain't coming back to school today.
Jaden, I'm not playing with you.
5 again.
I'm not playing with you.
Hey, can y'all stop the camera for me? It should still be running. Yep.
You know how to do this shit. I don't know. Ooh. How you do it?
Oh.
What was question 5 again?
Why would you want to